Our delicious mango has a thin layer of skin separating the inside from the outside. In a previous video, you learned how to mathematically describe the inside using interior points in the interior of a set. But now you might ask, how do you mathematically describe the skin of a mango? In this video, you will see how to use this mango to intuitively think about the definition of a boundary point, the boundary of a set, in n-dimensional Euclidean space. What is the definition of a boundary point of a set? Let S be a subset of n-dimensional space. A point P in n-dimensional space is a boundary point of S if, for every epsilon greater than 0, the open epsilon ball centered at P has non-empty intersection with S and also has non-empty intersection with S complement. Note that S complement is n-dimensional space minus S. Let's apply this definition to our mango. We will visualize our 3D mango with this 2D mango. We want to understand how to distinguish the edge of a mango. This dough will be our two-dimensional mango. Think of it as a set S lying inside of two-dimensional space. We have already chosen 3 different points in two-dimensional space, and we'll check if they are boundary points of S using our definition. Here is point A, point B, and point C. Look at the point B. Is it a boundary point of S? Intuitively, yes. It is on the edge. Let's check that the formal definition matches this intuition. For every epsilon greater than 0, the open epsilon ball centered at B must intersect both S and S complement non-trivially. This cookie cutter will create an open ball when I place it with the point B at the center. Looking inside the open ball, some of it is mango and some of it is not. In other words, the intersection with S and S complement are both non-empty. Does this mean B is a boundary point? Not yet. We technically need to check every epsilon greater than 0. I can place this smaller open ball centered at B. Looking inside this smaller ball, some of it is mango and some of it is not. I can also try an even smaller open ball and see the same thing. Because I will keep observing the same thing for every open ball that I choose, this will heuristically prove that B is a boundary point of S. Remember, we have an equivalent perspective. These cookie cutters allowed us to zoom in on the point. A smaller radius means we are zooming in more. We decided the point was a boundary point because, after zooming in enough, we will always see points inside the mango and points outside the mango. This idea gives an informal way to interpret boundary points. A point P is a boundary point of S if, no matter how much you zoom into P, you always see points inside S and outside S. Now, let's go back to our 2D mango. Is the point A a boundary point of S? Intuitively, no. It is entirely inside the mango. To check that the formal definition matches this intuition, we must negate it. There exists epsilon greater than 0 such that one of the epsilon ball centered at A intersected with S or intersected with S complement is empty. This open ball has points inside S and outside S. This does not prove anything. This smaller open ball at A has points only inside the mango and no points outside the mango. In other words, the intersection of this open ball with S complement is empty. This proves that A is not a boundary point. Notice we could have used any smaller open ball to prove the exact same thing. Finally, is the point C a boundary point of S? Intuitively, again, no, it is outside the mango. But remember, we must check the definition. There exists epsilon greater than 0 such that an open epsilon ball centered at C intersects S or S complement trivially. This open ball has points outside the mango and inside the mango. So again, it proves nothing. This open ball at C has points outside the mango, but no points inside the mango. So the open ball centered at C, intersected with S itself, is empty. We have therefore zoomed in enough to prove that C is not a boundary point of S. These examples suggest that we can formally define the concept of edge. Let S be a subset of n-dimensional space. The boundary of S, denoted del S, or also called partial S, is the set of boundary points of S. How does this apply to our mango? Recall we checked that B is a boundary point of S, whereas A and C are not. Continuing those ideas, any point along the edge will be a boundary point. Any point outside the mango or inside the mango will not be a boundary point. This means that our intuition matches our formal definition. The boundary of S will be the edge of the mango. There's also actually a neat observation. The interior of S corresponds to the inside of the mango. The boundary corresponds to the edge. These two sets can never overlap. This reveals another mathematical truth. The interior of S and the boundary of S are always disjoint. These ideas for our 2D mango translate seamlessly to our 3D mango. The boundary of our 3D mango is its colorful skin. In the next video, we will conclude this exploration to interpret the mathematical concepts of limit points and closure, using, again, our lovely mango.